Okay, but anyway, the idea is the following, right? So the crux of the idea is the following. So we are going to treat data points as nodes of a graph. So what is a graph? A graph is just an abstract way to represent anything, right? So relationships specifically. In this case, we can think of relationships among data points. So so what does a graph consist of? A graph is typically denoted using the letter G, and it has a bunch of vertices and a bunch of edges. So for example, visually you can represent a graph using a bunch of vertices like this, and there are these edges that connect certain vertices. For example, it can connect all pairs of vertices, it may or may not connect all pairs of vertices, right? So that's why we need what is called as E, which is an edge set, right? So V is the vertex set, and E is the edge set. So for example, in this example, let's say you have 1, 2, 3, 4, 5, 6. My vertex set in this case would just be 1, 2, 3, 4, 5, 6, because those are the 6 vertices of the graph that I have. I mean, I'm representing the graph using 6 vertices now. Now, what would be the edge set? The edge set is a set of sets. So for example, 1, 2 is part of this edge set to indicate that there is an edge that connects 1 and 2. 1, 3 is not, because there is no edge that connects 1 and 3, whereas 2, 2, 6 is an edge, 2, 4 is an edge, 3, 6 is an edge, 3, 5 is an edge, 4, 5 is an edge. So this would be the edge set 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, 6 edges, right? So of course, now I'm treating what is called as an undirected graph. So these edges don't have directions. It's when I say 1, 2, there's an edge that connects nodes or vertices. So I'll interchangeably use the name nodes and vertices. When I say that, they both mean the same to me. So when I say 1, 2, there is an edge that connects vertices 1 and 2. There is no direction to this, right? So, but there might be graphs where I might be interested in directions, where I can say there is a directed edge that goes from 1 to 2 and not the other way around. There is no directed edge that goes from 2 to 1. For example, your Instagram or any social media network where you have Twitter or X, right? So where you have this following follower as a relationship. So A follows B. That means that there might be a directed edge from the node or vertex A to the node or vertex B, whereas B may or may not follow A back, right? So which means that you may want to distinguish the direction, the relationship's directionality. But for our purposes, we will, at least for this purposes of clustering, where we are thinking of data points as vertices and and we'll define what the edges are in a minute. So we will work with undirected edges. So now how is this graph going to help us? So what we are essentially going to think of is we are going to think of, let's look at, maybe I'll draw that again, so that we'll still worry about this example for the moment. So think of this as now nodes or vertices. Each data point is now a vertex, and for every pair of nodes, so the edge, there is an edge that connects every pair of nodes, and sometimes what I might also want in addition to the edges is the weights, right? So this is the weights. So, not all edges are treated equally, some edges weigh more than some other edges, let us say. Now, what might happen is I might want to weigh the edges, right. So, now for example, so each of the data point is a node, and each of the there is an edge between any two nodes. For example, this might be this one edge that we may want to care about. Here is another edge that we may want to care about, and let us say here is another edge that we may want to care about. Now, what we want to do is assign some weights to these edges, and because there is a natural geometry to these data points, the weights can depend on this geometry itself. So, assign weights based on distances. But how exactly we will see, because I first have to say why are we doing this, right. So, what is the eventual goal by assigning these weights for every pair of data points? Of course, there is a distance between every pair of data points, and now why do we want to do this? Well, we want to do this because we want to think of clustering as cutting a graph into pieces. For the moment, let us say 2 pieces. Let us say we are worried about clustering into 2 parts, because this data set there are only 2 clusters, but in general k pieces, but for now 2 pieces. So, what does it mean to say we are cutting a graph into 2 pieces? Now, every data point is a node or a vertex. Now, I am going to cut the graph into 2 pieces, means that I am going to treat one set of nodes separately from the other set of, from its complement set of nodes, right. So, a cut is just a subset of nodes in the graph, right. And now I want to know what is the best way to cut this graph into 2 pieces such that I get the clustering that I want. Yeah. So, for example, in this case, an ideal way would be to cut the graph such that these nodes fall in one cut, one set, and then the remaining is in the other set, right. The cut is kind of, if the entire set of nodes, let us say if I call it as S, then this set of nodes, let us call it as A, and then there is a complement set, A complement, which is the remaining S minus A, right. So, A complement is just S minus A. When I say minus, set difference. Now, this is a cut, right. So, now this might be one cut, there might be k means might give me a different cut, right. So, for example, if I run k means, it would give me a cut which puts all these nodes in one set and then the remaining nodes in another set, right. So, I mean, if I want to treat k means as cutting the graph into 2 pieces, then the set of points which belong to one cluster that as produced by k means would be the cut that k means gives me. Somehow I want to say one cut is better than the other, right. So, what I am going to do is I want to somehow first of all define goodness of a cut, right. So, I want to say cut of A comma S minus A, right. So, is just the sum of the weights of all the edges that go across the cut. I am going to define this function as the sum of the weights that go across the cut, right. So, for example, in this particular example, let us say just to make it clear, I rename or rather I give names to these nodes. So, let us say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15, 16, 17, 18, 19, 20, 21, 22, 23, right. So 15, 16, 22, 23. So there are 23 nodes in this. Now what would k means, cut of k means that might produce, that would just be the set 1, 2 till 7. In addition to that, we have, let's say we will have 15, 16, maybe 21, 22, 23. So which is, these points, this 15, 16, 21, 22, 23, and then 1, 2, 3 till 7, right. So those that would be the set of points which belong to, which defines the cut. 23, and then we have the remaining, right. So 8 to 14, 17, 18, 19, 20, right. So now how will I define this? I will just define this as the basically the sum of the distances of, weights basically, right. So which means that for every pair in this cut, right. So which means I am going to take one and then measure its distance to everybody on the other side, right. So 1 to 14, 1 to 13, 1 to 12, 1 to 11, 1 to 10, and so on, and then also 1 to 17, 1 to 18, and so on, right. So that is there is some weight associated with each of these edges. The weights will depend on distance, which we will come to later. So I want to measure the value of the cut by the sum of the weights of pairs that go across the cut, or all the edges that go across the cut. Now it's up to us to define the weights itself, right. So once we define the weight, then we can ask, what type of cuts are we interested in, right. So the weights, right. So one way to define weights, right. So there are multiple ways to do this. Here is one way. Wij, that is the weight for Wij is the weight of edge I comma j. Now I am going to define this as, well, again there are multiple ways to do this. Here is one way to define this as e to the minus xi minus xj squared by 2 sigma squared. So what I am doing here is I am kind of giving the weight corresponding to the geometry of the points themselves, right. So what is this saying? So this is saying that if two points are far apart from each other, that is, if xi minus xj's norm, the distance between xi and xj is large, then the weight of that particular edge is going to be small, right. So similarly, if two points are very close to each other, then the weights are going to be relatively large, right. Now of course there is the sigma, which is like a hyperparameter, which kind of controls, how much are we increasing or decreasing the weights and based on the scale, right. So let's not worry about that for now. The more important point is that the weights is inversely proportional to, so basically, let me say inversely proportional to distance. So if I do that, then my question is, if I look at these two different ways of cutting the graph, one way is what k-means would give me, which would be, a cut where we have points, these points as one part, and these points as another. Right. So this is one way to cut the graph into two parts. Now the other way, which is something that we would want ideally, is this way. Now, here is a question for all of you, right? So, the way I have defined is, this is cut 1, let me call this cut 1, this is cut 2, and now I want you to think about which of these cuts will have a larger value when we in the definition of cut that we have given, where the weights are inversely proportional to the Euclidean distance of the lines joining the points. Pause the video, think about this. Let me talk about which of these would actually be larger or smaller now. So what's happening is, we have two different cuts, and we are interested in knowing which of these cuts would give us a larger value, right? So let's consider this cut, for example, the cut 1, for example, right? So here, if I take one of these, or maybe I should take an extreme case to illustrate this better. So let's say I take one of these nodes, right? And I can do this for both of these. Let me use a different color. No, I'll take the corresponding node here as well. Now I want to measure the distance or measure the weights, sum of the weight, how much does this node contribute to my cut, and that is just the weights to all these guys, right? So all the red guys basically. Similarly, this red guy is going to be now measured with respect to all the green guys, right? So now, as you can see, right, so which of these, right? So as you can, I mean, first of all, if you just look at, I mean, visually, even by looking at this, you will see that the gray lines in cut 1 are larger, right? So they have a larger value to these red guys. So to these red guys, exactly that's the same thing that this will also contribute. The extra that it is contributing is the distances to these guys, whereas in cut 1 it is to these guys, right? So which means that the amount of contribution from this would be, let's say this is node A, and the amount of contribution, so contribution of node A to cut 1 versus contribution of node A to cut 2, so which do you think is larger, right? So because we have defined the weights as inversely proportional to distances, so node A has a larger sum of distance to people in the other, other piece, so it will contribute lesser to the cut than what it contributes, cut 1, than what it contributes to cut 2, right? So basically contribution of node A to cut 1 is lesser than what it contributes to cut 2, because the points are on an average closer. But this point, because of the symmetry here, right, so of the points themselves, then it's not, there is nothing special about, any of this point node A that I took around the circle, at least the outer concentric circle, right? So that's kind of going to give me the same, I mean, pretty much the same value, right? So for any of the points that I take in the outer circle, so for all the points in the outer circle, then they will contribute more to to cut 2 than to cut 1. Now, what can you say about a point in the, in the inner circle? So let's say I take this point as my point of reference. So what does this point contribute to in terms of its contribution to cut 1? Well, I use a different color. It's going to be the sum of this plus these, everybody outside, For this it will be, you know, just the sum of everybody outside, right? So now in this case what's happening is, so this point, the inner point, is going to suffer the same amount for these inner points. Is it correct? Yeah. So this is all in the same thing. So now for the, so it's going to suffer a distance to these things which are same in both, but it's going to suffer a larger distance to all the left hand side of the circle, which it will actually avoid in the other case, right? So because that will get replaced by these points in this case. So it will probably have, you know, so it will the distance, the sum of, I mean the total distance sum will be lower, right? So here, so let me say that again. So I take this point. So what is common is this region, which we don't have to care, right? So the contribution is going to be the same. Now what is different? So this is common, and what else is common? This part is also common. This part is common, so this is red in both, this is green in both, so we don't have to care about that. So here this is green and that's not being calculated. Instead of this set of green, we have this set of red coming in here, right? So which means that the sum of the distances, you know, the distances are larger, so the weight, sum of the weights is going to be smaller for cut 2 for each of these points, whereas here the distances are smaller because of correct. So because of these red points, and so the weights are going to be larger. Some of the contribution is going to be larger, right? So the notion will flip in for these inner data points. Now the question is, what do we want, right? So we are trying to cut the graph into two pieces. Now if you look at the if you look at the sum of the weights of edges that go from one cut to the other cut, do we want it to be larger or smaller is the question. Now we are going to define, I mean at least we are going to think of intuitively a cluster as, you know, you have a cluster and then there is this other cluster which is outside. Ideally, you know, you want the other cluster, whatever that is, right? So you want to cut the graph into two pieces such that, you know, this average distance or the sum of the distance to the other guys should be larger, right? So they are all away from me, but the weights, if you look at the weights, then the sum of the weights should be smaller. Now that does not necessarily mean that the graph is going to get exactly cut like this, right? So there may be a different cut of the graph such that if I look at the sum of the weights to the other piece from the piece that I have in my hand is smaller than the piece that K-means might give me, right?